All right. Welcome to Unit 7-4, Areas of Trapezoids, Rhombuses, and Kites. Please write the following theorems down, Theorem 7-10 and Theorem 7-11. If you need to stop the video to write these down, please do so now. Okay. Example 1, we're going to talk about the Theorem 7-2, the area of a trapezoid. The formula is listed below the title. Area equals 1/2 times the height times the base 1 and base 2 added together. So let's first talk about what the height looks like in any shape. When you're referring to a height, it's the distance from one base to the next base. It's always labeled with a 90-degree angle because height is straight up and down from one base to the next. In our example, the height would be the 16 inches located right in the middle of the trapezoid. So to start our formula, I'm going to go ahead and write A for area. And that equals 1/2, so 1/2, times the height, which is 16. And then the next part of the equation talks about base 1 plus base 2. Now really base 1 and base 2 could be either parallel line. The parallel lines are located, on our example, at the top and bottom. So we're going to be using both the bottom value, 38 inches, we'll call that base 1, and the top value, 21 inches, we'll call that base 2. Now I could have chose 21 to be base 1 and 38 to be base 2. It really does not matter which one you label as 1 and 2. But we are going to add those values together and multiply that by what we already have in our equation. Okay, so we have our equation written out. We have the area equals 1/2, 16 for the height, times the sum of the base 1, which is 38, and base 2, which is 21. All right, the next step is to just put this all in our calculator. If you're having trouble with the fraction of 1/2, you can change that 1/2 to 0.5. And just remember that you need to have parentheses around the 38 plus 21. If you don't put parentheses around it, you will get a different answer than what we're getting. My answer was 472. And to complete the problem, we'll put our units on the end, inches. And area always is in squared units. So it's 472 inches squared. This is our final answer for example 1. Okay, moving on to example 2. Again, we have our trapezoid. It's looks slightly different. It looks upside down compared to the previous one. And they also added some extra numbers that just kind of throw you off and confuse you a little bit here. I'm going to go ahead and cross off the values that we don't need to solve this. So first off, we know we need the parallel lines. So our parallel lines are at the top here and at the bottom here. So we definitely need those because those are our base 1 and our base 2. All right, the other value that we need is our height. Well, our height is always connecting base 1 and 2. So that would be this value of 13 here in the middle. That would be our h, our height. All right, the other two numbers in the problem are just there to throw you off. I'm going to go ahead and just cross those off. We're not going to use those. Now we have the three values that we need. We're going to go ahead and plug it into the formula listed above. So that would be area equals 1/2 times the height times base 1 and base 2 added together. Okay, so we have our formula. Now we just have to plug this equation into our calculator. Make sure you include the parentheses, and you should get. Okay, and the answer I end up getting was 179.4. And just to keep our units on there, we had kilometers squared. Remember, our area is always in squared units. Okay, on to example 3. All right, example 3 is a different theorem. It's theorem 7-11. It's the area of a kite. The formula for the area of a kite is 1/2 times the diagonal times the second diagonal. The diagonals are always located within the shape, so in the middle of the shape, from one vertice or corner to the other vertice. All right, so in our example, I'm going to go ahead and trace over our diagonals. Our first diagonal goes from left to right across the shape. And our other diagonal goes from top to bottom through the shape. Now, it does not matter which one we refer to as diagonal 1 and diagonal 2. We just have to come up with both values in order to plug this into our equation to get our right answer. So the equation again is area equals 1/2 times diagonal 1. Now I'm just going to go ahead and call diagonal 1 the one that goes vertically. And if you notice, it has 3 and 3 for both parts of diagonal 1. So we do have to add those two values together. So 3 plus 3 equals diagonal 1. So it's 6 for diagonal 1. And diagonal 2, we're going to go ahead and call the horizontal diagonal. Again, it doesn't matter which one I call diagonal 1 and 2. We're going to do the same thing here. We're going to add the two values together. In this case, it's just 2 and 4. And it's just a coincidence that diagonal 2 does equal the same thing as diagonal 1. It doesn't always work out that way, but it did in our example. And then the last step here is once we have each part of our equation, we can just plug it into our calculator and come up with our answer. The answer we should have gotten was 18. And it's meters squared. All right, so our last two examples both share similar formulas. They're exact same formula, but the shapes are slightly different. Let's look at them. All right, for example 4 here, we are finding the area of a rhombus. Now, rhombus and kites are very similar. They have similar properties. The formula to find the area are exactly the same. So again, it's area equals 1/2 diagonal 1 times diagonal 2. All right, in this case, though, With a rhombus, we have to remember that the diagonals cut each other directly in half. So in other words, when we look at this shape, we see that one diagonal goes across like this, and the other diagonal goes across like this. And where they intersect cuts each one of those diagonals directly in half. And so what they gave us was only part of what the actual diagonal equals. I'm going to go ahead and write in the other part. So our first diagonal here, we'll call diagonal 1, is going to be equal to 20 at the top of the diagonal, but also 20 on the bottom, which means our total diagonal is going to be equal to 40. Because 20 and 20, we add those together to get our 40. We're going to have to do the same thing with our other diagonal. So we have 30 on one part, and our second part here is going to be 30 as well, which means the total is 60. Now that we have the total for both diagonals, 40 and 60, we can just plug them into our equation. So area equals, again, 1/2 40 times 60. And we can plug that directly into our calculator to get our answer. And what I ended up getting was 1,200. Okay, so that's our rhombus. Our rhombus, like I said, is very similar to a kite. The equations are the same. However, to go about getting the distance of the diagonals, we do have to look at them a little bit differently. All right, our last and final example, it's also a rhombus, but it has a little bit of a unique twist to it. So I'm going to go ahead and click over to that one. You'll notice in this one that one of our diagonals is labeled with 8 inches. The other diagonal, though, has nothing labeled. So we'll call the first one diagonal 1. And it's labeled with 8 inches. And again, the other side's going to be 8 inches. Now we can't assume that the other diagonal, diagonal 2, the one that goes vertically, is the same. It's not the same. But in order to figure out what that small part of the diagonal is, we're going to use the Pythagorean theorem to basically find this missing part of this triangle located in the top right. All right, the triangle looks like this. I'm just going to redraw it over here. Right, this is our diagonal 2, at least half of it. This is the side that they gave us, and this is the 8 inches, which is half of our diagonal 1. Now, if we're using the Pythagorean theorem, we know that this is a right triangle, and we also know that the side labeled with 10 inches is our C, because our hypotenuse is always located across from the 90-degree angle. All right, we also know that our 8 can either be written as A or B. I'm going to call it B this time, and I'm going to call our missing part A. And now we're going to be able to use the Pythagorean theorem, which is again A squared plus B squared, which in this case is 8, equals C squared, which in this case is 10. All right, and then we go through and we solve this problem. You can use your calculator for these calculations. We'll subtract 64. We end up with A squared equals 36. And then don't forget to square root at the end. So A ends up equaling 6. Now remember, A is not our entire diagonal. A is only half of our diagonal because A just represents this portion right here, which is 6. We also have this portion of the diagonal, which is also 6. So to finish this problem, we're going to add both halves of our diagonals together. So diagonal 1 and diagonal 2, we're going to add both halves together. So diagonal 1 would end up equaling 16. Diagonal 2 ends up equaling 12. So we're adding the 8 and the 8 and the 6 and the 6. And now we have our equation that we can plug in to our calculator. And I end up getting 96 as our final answer there. Okay, so that is our last example. Number 5 is definitely the hardest example. If you need to watch it over, just kind of rewind the video and replay it. Um, uh, for the next slide, I'm going to have you try a couple examples on your own. So the following 4 examples, go ahead and attempt them on your own. If you need to pause the video, do so. And then the answers will be at the end of this video. Remember, you can always rewatch these videos at modo.com. And if you have any questions, ask your peers around you for help.